Welcome back to this Hough transform that we are discussing from the last two classes. In the last two classes, what we did is we have seen how parametric shapes, that two particularly we have looked at detecting the lines which can be parameterized using a particular transform which is referred to as Hough transform here, where we are moving from the representation of an image space to a transformed space which we refer to as parametric space or Hough space as well, where let's say we want to detect lines. Line can be parameterized by its slope and intercept. So this parametric transform which we are doing there, in that parametric in coordinates or in that space, parametric space, what you have is rho and theta. And we noticed that all the lines that are passing through a given point would constitute to a line in the parametric space. Similarly, if you have a line here, that would correspond to a point in this parametric space. Then we realized there are certain issues with representation of a line using slope and intercept. What was the key issue there?
We were not able to recognize vertical lines.
That's right. Vertical line has an infinite slope, which cannot be considered. So we move to another kind of a polar coordinate representation of the line, and then that problem is no more there, right? That's what we did till the last class. And let's say you have an image like this for which you want edges like this. Okay. So if you move into the parametric space, where, well, even if you find out, let's say, a canny edge detector, if you run on it, you would be getting something like this. Okay, this is a very toy example. So canny edge detector could itself do a good job, but then assume that there is some noise also. Okay, by the way, this might give you something like this in your Hough space. And suppose if there is certain noise also there in this image, you might be ending up with something like this. But still, when you put a threshold on the number of votes for each row data cell, you would end up with something lines, something like this. What was the very dominant problem here that you observe while computing, while giving you edges using the Hough transform like this? What is the very critical problem? There are indeed quite a few problems you could say there, but I want you to tell me what is the biggest problem there.
We got false edges.
We got.
False edges.
Yeah, false. Can you say what exactly you mean by saying false edges there? You are worried about this part, right? And this part,
Some parts which are intersecting the diagram also.
which are intersecting the diagram also, right? Yeah. Can you be that is one thing that I understand, that that's the first answer as well. So what I would see is, other than intersection, there is some other problem is also which is quite evident here. If I give you this and ask you to improve it, what's the things that you would prefer doing? How do you do? Forget about it. But what is that you would like to do? You wanted to find out, I asked you to find out edges on this, and I gave you Hough transform algorithm. You got it. You got this one. Now I'm asking you, what is it that you would like to do it to further get the right edges?
Inside the diagram, there shouldn't be any edges. It should be only
Right.
along the line.
Is it just inside? Isn't there anything other thing outside?
So we should get just a line segment, not a whole line.
That's right. That's right. That's what I was expecting. I want my edge to just end here. I don't want, of course, you are right. Inside, I don't want it. That's a very valid point. I don't want this intersection inside. That's also is a valid point. There should not be so many lines. It should be ideally a single line. That's also is indeed true. But even more than that, what I would say is this line should just start there, end here. Similarly, this line should just start here and end here. Not, this should not be there. Similarly, this line should just start here and end here. Now, should we just throw this Hough transform algorithm out and start afresh for yet another new algorithm? That's one possible way you could think of. But I would rather ask you, what is that you do to this Hough transform that I would simply get these edges that are there in the middle image. That's what I want. So what is the modification that you could think of, you can make to Hough transform to arrive at these edges instead of these edges? So this is a very simple example also, which would allow you to come up with some solution. Okay, assume that there is no noise in the image. Okay, uh, then of course this what I know the previous answer that one of you are telling is multiply this with this and just get these things be there. Well, that would work in a very ideal scenario. If that was the answer you are thinking, would work in a very ideal scenario where you already have the edge here, and then you don't even have to go to the Hough transform space.
Sir, we can draw a line limitedly such that it will be drawn only between 2 points which satisfy in Hough transform plane.
Very good. You are almost close. Can you refine that? How do you know from where to start and where to end? That's the question. Very good. You are in the right thinking in the right direction. But now you tell me, I gave you this image, right? And I give you this image also. Assume that here some parts are missing. There are some white spots here and there. That is there. Okay. Now, from that, I want to arrive at, okay, assume that this is your final answer. Okay, maybe I'll show. Yeah, assume that your this image, for example, you take it. Okay, this is how your canny edge detector has given you, you thresholded it and you got this. Now, and assume that there are also some points here and there, noisy points are there, just like they were there in this image, and along with that you have this image. Now you tell me, and now think in terms of some edge linking problem where you have here edges in a conservative way. What I mean by that is, if at all something is there, it is very likely you might be missing some portions of it, but nevertheless you have somewhat a good sampling of your lines. So edge, in terms of edge linking, now you think about it, you have this. Okay, and you have, even this is fine for you, for me, I give you this, I give you this. Now I want you to just keep this line from here to here, keep this line from here to here, keep this line from here to here, by looking into both. Okay, this might not be, some breaks could be there here, like for example this might be missing, then it might be starting here, it might be starting here, some breaks are there. While you do the voting, in case of Hough transform, while computing your Hough transform, for each cell while you are voting, you would also make a note of which is the point that is voting, okay, for that particular cell. This is the additional thing I am going to, this is the modification I am going to do to the Hough transform. In the normal Hough transform, I was doing a simple voting. I cannot backtrack. Suppose I found that there is a line in this. Okay. Now I could get only this line there. Suppose after voting, when I am doing thresholding a number of votes, I could get just this line there. But if that is passing through it or up above the threshold, but I could never know which of the points in this image have contributed to this line. Now, in with each vote, I am also going to say who has made contribution to or voted for this particular cell. Now, can you think of something?
Now all we have to do is just gather those points, and that will be an edge. We just need to plot the edge only
See,
from that
gathering
maximum to
just those
minimum.
points might give you, let's say, some noisy point could be there somewhere here. Okay, let's say in this is the line I want to find out. There could be a noisy point somewhere here, and here maybe 2-3 points might be missing here. But still, I want a line here, knowing that this is a line. And although on this straight line there is a point here, I never want to extend it till here. I'm giving you the hint also. Say here very closely some point is missing in between. Okay, this I want to put it as a line, and there might be some point here lying on the same straight line. I don't want the line till here, although there is a point here. Now you tell me.
Sir, we consider only the lines in the Hough transform that are close to each other.
Lines are something else.
The curves.
Not the curves. No, I give you now. No, I start from here. Okay, I know that with so much value of rho and theta characterized by that there is a line, okay, that I have given you. Now with that information, I want there could be some missing points here, okay, something like this could be there, some missing points here, some extra points here, but I want it to be just like this. That's my objective.
Sir, we can take all points which voted for a line and
Right.
arrange and sort them in increasing or decreasing order, and
Okay.
eliminate those points which are more distance from the other points,
Yeah. Okay. Very good. You are
and
80%
plot
there.
from
Yeah. Very good.
minimum coordinate to maximum coordinate. Limit the line between them.
Right. Very good. You are almost there, except that sorting points is not something that you could do. What you would in fact do is you would look at distance from the nearest point to the next point in that line. Okay. Okay. Well, sorting also you could think of, if the line is like this, then you could put all these points here in the sorting and see to the next point how much is the distance. That's what you mean, right?
Yes, sir.
Very good. That's what you would do. Okay. So I will, so let's say here you obtain a thresholded edge image here. Okay. That's what you would get, something like this. And after that, specify subdivisions in the rho and theta plane. So this is to get your Hough transform, Hough space getting the image. Now examine the counts of the accumulator cells for high pixel concentrations. Okay, this is what you would be, yeah, well, just a small correction to the earlier statement also. I don't really need to, one way is I could keep track of points that voted. Even without that, once I get the line, okay, I know which are all points that are close to it. Of course, keeping track would make my job easier because that might be slightly away, or that also is okay even without keeping track of that. Okay, this would also work out where uh, you just look at all the points that are there on this line, and to the next point you look at the distance. If the distance is within a particular limit, okay, this limit is again an empirical thing you have to choose depending on the context. Then if it is within that limit, the next closest point is within that limit, you keep that, or you, in other words, you are linking them both while drawing the line. Otherwise you are going to drop that. That's how you could end your line. See here, suppose if you have something like this, then you could simply would be stopping here. Of course, there could be an instance where there might be a point here and that might be slightly coming, but all these things you could still, assuming that the noise is not very severe, you could simply get this line here, and similarly the other lines. So this is an example. By the way, are nothing new that we are discussing. This is the regular conventional basic Hough transform algorithm that you are seeing there. Now this is an example where they know this is the runway for a in an airport, where they know that this is the airport. Assume that for some reason, for of course for keeping track of things, first you want to extract the runway. On top of it, you are going to implement certain algorithm. So first step here is to get the segmentation, you call it, maybe segmentation is not the right way, just you get the region of the this runway. The prior information you have is this is the longest line among all possible lines that you can draw. If you are doing, let's say this is the top view of the runway in an airport, and if you are doing a canny edge detector, let's say this is where you would be ending up, and after that you do a Hough transform, and after that you select just one, the max, the that per only one cell that has the maximum number of votes. Okay, and after that what you need to do there is you look at this link edging. So within that line and your canny edge detector output, you see on this line which is the farthest, which is the next closest point. If that distance is beyond a particular value, you just stop the line there.
So, just to like clarify on what's
Yes.
going on. So we have an original image.
Ah,
We form an edge like okay, we find an edge image using Canny's
right,
algorithm.
right,
Then what exactly are we like
right.
adding this extra line
After
here for?
after you get the line, you look at this line, you compare this line with the output of, again, see, from the Hough transform, you do the voting, you select that line parameterized by maximum number of votes. That will put a line now starting from here till here, is it not? Hough
So
transform
you're
line,
trying to detect the airport here, is it like a
no,
runway?
the line to not detect airport, the path on which what do you call it, runway.
Okay,
This is
so we are trying to detect the runway
runway,
exactly.
right? And the prior information you have is that is the long. If you see in terms of lines from the top view, it looks like the longest line. That's what we know. If you just use Hough transform, it would give a line starting from here till here. Of course, sorry, the drawing went crazy, but that's the straight line you have. Now, instead of that, I want the line to be there from here to here only. Not this part I want to remove. So what I'm going to do now is this line, again, I would compare with the canny edge detector. And on this line, I would see the distance between the points that are there. Okay. Here, if you look at, there is no point. This is a, remember that, note that this is a binary image. So there is no point in this region. Similarly, here in this region, there are no points as such. Okay. Although there were some points that are a bit far. So this part, then you could get rid of it using the Hough transform. Now combining Hough transform with the canny edge detector in this manner.
Yeah, okay, sir.
Sir, so while maybe computing the edge, the line exactly, line segment exactly, so we first interpose, we put the line on the canny edge detector, and then see along the line the neighboring points,
Right.
and we see where the points are there and not there.
Right. That's right. That's right. Or I think there is no harm in actually doing what I was mentioning earlier. Perhaps that makes implementation of your algorithm very simple, where you now know which cell is corresponding to this line. Okay. Right, this you would get it by the end of doing your putting a threshold, and after that you simply go through all those points which were contributing to that particular cell. Okay. And then you see, you would see that in this region, so you just take the starting and ending point. Beyond that, if the distance to the next point that is there, even there might be some noise, like here there might be some point here coming because of some other thing going on here, but if the distance is more, you just drop that. I think that's an easy way to keep track of things, rather than again starting afresh and looking all the points in the canny edge detector. That brings down your complexity of your algorithm significantly while doing this modification.
So, sir, we when we if we keep track of it, we'll also need to sort it, right? Because we need to check the distance between adjacent points. Uh,
Yeah,
do we have to?
perhaps yeah, see, all you need to do is, in a way, yes, because all you need to figure out is the distance. What is the point that is closest to the point that you need to figure out there? So that's how. So see, distance between disconnected pixels. Okay, a gap in the line can be bridged if the length of the gap is less than a certain threshold. So in a way, I would say yes, you need to sort them out. So then only you would know the distance between the pixels. Okay. Or you could see it a slightly different problem than a sorting problem. You could phrase it differently also, where from this point you compute the distances to other points. And then if the distance is below a particular threshold, you put this point, you keep that. Otherwise, you ignore that. You can see it in both ways. So the next question, which I asked you to contemplate about it in the last class, is, let's say you have an image like this, okay, which you will be having soon in the next assignment, and your canny edge detector or some other combinations of edge detectors you come up with would give you something like this, out of which I just want to have edges like this. I'm just superposing my final edges on this image to show you clearly that these are indeed the circles. So how do you achieve it in similar lines? By moving from the image space to a Hough space. That's the question. How do you do that? So just line has intercept and slope. How do you, what is the way you want to uniquely characterize this circle? So what are all the parameters you have to give? This is a very trivial question. This is all you have to say is where is the center of your circle, and then you tell what is the radius of the circle. That's all, right? I want to draw this circle, for example. You should say the center is at so and so xi comma yi. At that you draw a circle with radius r. Okay, let's say the center is a comma b. Okay, a in the x direction, b in the y direction, and the radius of that circle is r. Okay, now what is the equation that parameterizes this circle? Can you tell me the equation? I give you that the center is a comma b and its radius is r. Okay, now you tell me the equation that parameterizes this circle, all the points on this circle.
X minus a whole square plus y minus b whole square equal to r square.
That's true. X minus a whole square plus y minus b whole square equal to r square, right? This is something you studied in your +2 or even in 10th standard. So where you want to get all the points that are there, let's say on this circle. Now for these points, if you are doing x minus a whole square, okay, so for this, suppose this is with radius r, so this would be characterized by any points. If you take, if those points which satisfy this equation would be those that are there here. So in other words, x minus a whole square and y minus b whole square is equivalent to shifting the origin to the center of the circle. So assume the case to understand, to get a feel of this equation. Okay, assume that what I'm drawing is also a circle there. Suppose this is your center is 0 comma 0. For all the points that are there here, how can you characterize that? X square plus y square equal to r square here. Okay, r equal to square root of x square plus y square. In other words, those points of x and y for which square root of x square plus y square is equal to r, all those points will be on the circle, right? Now you have a shift in the center because the center is at a and b, not at the origin. As simple as that to understand this equation. Now you tell me, you some algorithm through which you could find, given this image, you could come here and get these circles. How do you do that?
Similar to the line, sir. Half
Right.
transform plane.
Right. Tell
But,
me step by step now.
but it will be a three-dimensional plane, sir.
Very
R,
good.
C,
Yes. Yes.
R, A, and B, sir.
Right. You tell me in steps. You are absolutely right. Now you tell me how you do that. So it is in fact a three-dimensional array now, right? That's what you have here. Let's say you could vary now A, you choose B, okay? You discretize here the A values. You discretize similarly the B values here. And for a given A and B, right? So is it A and B? And that statement is wrong. These are, do they represent A and B? Whatever you are discretizing, what is it that going to represent? Yes, in fact, A and B. X and Y you get from this, those points which are there here, non-zero in this binary image, those are your X and Y points, right? For those points, you take a particular value of A and B here, okay, all possible values, you have a grid there. And given those A and B, you compute what is the R value there. So R is square root of x minus a whole square plus y minus b whole square. X and y you get from this image. And in these cells now, okay, you have here in that particular x of, now you have a, let me just use this notation here. You are calling this array as capital A. Now you go to A of A comma B, that is what you are choosing. Now you got some C value here. Assume that this is also a quantized value. Now at that location, you increment its value by 1 there. You have, instead of a two-dimensional array, you have a now a three-dimensional array, and you repeat this. At the end, choose that value of A, B, and C, which got maximum number of votes. Or you put a threshold, anything about that threshold, all of those parameters you consider as circles, that would in fact give you something like this. Right? Is that clear? Are any questions so far? And you have to do it in your assignment. The next assignment is on the way. Just within this week itself, it will be uploaded. So this is something you are going to do, and again implement it from scratch. So this has to be very clear to you.
Sir, just a question. So,
Yes.
are we like, is it like more of a brute force method where we check all possible values of A, B, and see which one is getting the most number of votes?
Yeah, in a way, I would say yes. You are looking at all combinations. That is in fact true for all these Hough transforms. But again, there is one more beauty of this Hough transform is it will simultaneously compute all possible circles. That's the beauty of it. Compared to that, see, what I would rather call it as a brute force is, suppose in a given image, if I am considering for each point all the lines that are going through it, okay, and then looking at votes, and if I am getting it, that is even more brute force. If means I cannot ignore calling this as in a way brute force, because you are looking at all combinations, but that's even more more forcefully or more hectically done. On the other hand, here, see, at the end of your algorithm, the moment you keep a threshold on the number of votes here, the nice thing that is happening here is you would get all circles. You might be having, let's say, 50 circles or 100 circles in your image. All of them you would get it in one go. Is that important advantage of Hough transform is clear? While definitely this is a brute force thing, that I cannot deny that. Is that answering your question?
Sir, just one more doubt on top of that. What
Yes.
happens is there's like a circle in the corner of the image. Like there's not a
Circle is
complete circle, but like there's not like the image that you showed there. It had three circles that were like fully visible.
right.
Instead, we have some circle lying on the edge, like only 3/4 is visible, or some half
Okay,
circles.
okay, yeah, yeah. Those problems are
That
always
case
there.
doesn't work.
Right. No, those cases, as long as it is getting enough number of votes, votes are the ones which are the points here. So your question is something like this. You have a point, sorry, you have something like this, right? Yes, a coin is
Yes, sir.
assume
Yes,
is
sir.
like this, your image is like this, then what would happen is your question, right?
Yes, sir. Yes.
Yeah, it does has a problem there. It is not the only case where it faces some problems. Assume that there is one more coin here which is falling on this. Then it might end up with giving something like this rather than giving them and identifying them as two cycles. This even more prominent problem here. Whenever there is an overlap between circles, that's also is a very tricky situation.
So how do we find the centers of the circles?
We don't find centers of circles. You find at the end when you are doing the voting, the votes, number of votes that you got has this A and B and R values. Just like at the end of your line detection, you have your rho and theta or intercept and the slope in the other way of parameterizing. Here also that would give you already A, B and R. That itself will help you to just draw that circle. Isn't it?
So essentially, we are considering all possible radius in this.
That's right. Just like in a earlier case, I am considering all possible slopes or all possible theta values there. Here I am considering all possible, I would say not A, B, R. I am considering all possible centers here, because here I am varying A and B. I am looking at what are all the corresponding R values there. I am looking at. So what I would say is you are considering all possible values of centers. So you have 3D parameter space you are in. You initialize the whole 3D array into zeros, and then if for every xy where the gradient value is above a particular threshold, then you go through all possible values of A and B. For all possible values of A and B, you are going to compute the corresponding C value, the radius value, and then for that particular C value, of course, to be more precise, I should be quantizing it to the nearest one, depending on what all values I have considered. And then that that array location, again, I should convert the value to the index where it is stored also. That also I have to do something there, but this is just for your quick understanding. So that's an implementation detail you have to take into care while you are implementing this in your Python or MATLAB or whatever, that you are incrementing it by 1 there. Is the algorithm clear? Okay, so if it is clear, now I have, let's come back now again back to the line. Okay, just like we say back to the square one, we will let's come back to the line. Now, earlier, while finding out lines, you were using just the information of magnitude of your gradients. Now, what is it that the orientation of your gradient there is telling you? And is there any way to further simplify your algorithm where you could effectively use this orientation of this line, orientation of your gradients at a given point? Is my question clear? So in all your algorithms, even you take, I don't have immediate, yeah, it's okay. I could take a figure here. Here, I just want to consider, earlier it is only the magnitude I was considering. Now, since you have another important information of gradients also, gradient orientation also in addition to the magnitude of these gradients, what is the orientation information would tell you?
The direction in which
In which the
there is
edge can be
maximum
there.
increase.
Is it not? It gives you the information of how the edge could be there. Is it not? Then why to vary all the directions? So if I am not wrong, rho equal to x cos theta plus y sin theta. That was the equation of the line, is it not? Now, can you somehow use this orientation you got it also instead of in addition to the magnitude, you have orientation as well, right? So in what way can you use this information? You just look for edges in that particular direction only. You don't have to look everywhere. If there is a point here, if its gradient is in this direction, you just look for edges in this direction itself. So it would reduce your parameters by 1. Okay, so that's what you would in fact can do while implementing these algorithms. I'll just jump here and show you that here. So you compute this gradient dou f by dou x and dou f by dou y, and you are getting the theta value here. And once you got that theta, look at here. So for each edge point, right, you know the theta value. For the given theta, you compute the rho value and you just increment that. You don't have to say, for example, if you recollect, you have a 2D array that you are going to populate with the values you are getting. Suppose you might be varying theta here on this and you are varying rho. Now you know the theta here from the gradient information. So you just take that particular theta here. Okay, for example, for a given point x comma y, which comes from your edge image or gradient image. For that, you know the rho value, you compute it for x naught, xi comma yi, you compute it, and you just populate that. That's good enough. That's how you could use the information of the gradient, so that it reduces the degrees of freedom by 1, the number of parameters by 1. Is that clear? Yeah, so this part hopefully is clear to you. Then this is another nice thing. Okay, you might not need to do this, but suppose you are just using a binary image here, why not actually make use of the strength of that magnitude of that gradient, so that instead of just incrementing every time by plus plus, you could in fact do it by, if the strength is very high, you give more weightage there. While you are adding it, you give more weightage there. So how you give more weightage, for example, is by normalizing it in between 0 and 1. Okay, highest magnitude of gradient, if you give 1, half of that you give 0.5. Okay, even half of that you give 0.25. So instead of doing plus 1 here, you would be incrementing it by, let's say, w. W is a normalized magnitude gradient. This is another possible modification that you could think of for Hough transform. Okay, there are other things also. Okay, in the interest of time, I would leave these two, where you could say changing the sampling for this theta and rho in a way is equivalent to looking at different resolutions. I would leave it to you for contemplation. Okay, similarly, if you might be looking for squares, that lines also would interfere with it while you are doing the voting. So this is a bit more advanced. So for now, you ignore that part. So just to summarize with pros and cons here, the pros of it. Okay, so please, those who have a class, I would anyway wrap it up, but you have to, if you have to move, please go ahead. I will anyway share this video. Okay, the wonderful point, the biggest advantage with Hough transform is all the points are processed independently, and all these parameters, once you populate, once you completely go through all the non-zero points in your quantized gradient image, and then you put a threshold and number of votes at one stretch, you get all of them. Okay, and then some robustness to noise is also there. As you could see, you could be very conservative while choosing the edges in the gradient image by putting a very high threshold, because even if there are, let's say, some gaps here, since all these points would contribute to the votes, you would eventually get a line here parameterized by. So you can be very conservative, and although there are some points here and there which are, the noise is not forming the shape that you want, as long as that's there, yeah, it will not worry about that. Just that you would be getting a very populated Hough transform space like this. But once you put a threshold on that, you would end up with choosing those points which would contribute to the line. So this has a lot of robustness to the noise. And then this is something that the good thing is, some of you had identified this in the very first class on what would happen if your quantization of your theta and rho is very coarse versus very fine. If it is very coarse, what it means, suppose at a particular point you might be having two lines like this, but if you are too coarse in your sampling, these two theta values, small incremental change delta theta, if it is below that, all of them would contribute to a single line there. So sometimes it could put together, everything put together might be giving you, it's like two parties merging at the end, might give you more results than one party which hasn't merged and which has a genuine votes there. So that could happen when you are going too coarse. Suppose when you are going too fine, the other kind of things could happen because of the way it is acquired and because of the way that's computed. Maybe some other line could pass through it, but in fact this might be a single line here. Okay, so that would give you more number of collinear, or you might be looking at some collinear lines that are there. They will all get yeah, in some case, in the coarse case, they get merged here. And you are going too fine, you get multiple lines where you are supposed to get a single line. Okay, and this also we had discussed. Good that some of you yourself have noticed and suggested this, is you vote for neighbors also, so that it brings a smoothing in the array, and that would eventually would give you better results. And utilization of the direction of edge would reduce the parameters by 1. This we have seen just before going through this thing. To read back which points voted for winning peaks, keep tags on this vote. So this is something we had already seen before in the beginning of the discussion, where we are doing the edge linking. So those are the practical tips that you could do. Okay, I think I moved both pros and cons as well. See, the one big disadvantage of the Hough transform, again some of you had pointed it out, is it's a kind of a brute force stuff, where the number of parameters are increasing. See, circle, you had 3 already, so you have a 3-dimensional space. Suppose you have m possible values of so the and m and n possible values for a and b. Okay, then it is already the, and let's say some o number of values, quantized values that you are giving for radius. This is already m times n times o. So just to assume that all are same, so this is order of m cube it is going, and it was order of m square in case of a line. And then think of what would happen as you are moving and increasing the number of parameters there. So that's something, it, as long as your degrees of freedom are less, this is excellent. It could go at a one stretch all shapes that are of that particular shape in a given image. But the moment the number of degrees of freedom are increasing, this goes exploding. Okay, quantization can be tricky. So non-target shapes also we discussed just now. Okay, so again, just the last slide here, which we will not go into detail, just a pointer that I wanted to give is, suppose you have a template of it, the shape, which you might not analytically quantize, but numerically you could say that this is the mean shape of it. Then there do exist algorithms. This particularly this Ballard paper is a very well-known paper that started doing this. Is if you have a template shape, that template shape can also be incorporated, and you could get all such shapes in a given image by adapting or modifying your Hough transform concepts that we discussed earlier. Okay, with that I'll stop Hough transform. Hope this is clear, and we will start with a new topic from the next class on Wednesday. Bye, take care.